Ilham, just to check from your side, can you see, is it being recorded? Ilham,
Recorded. How do I know it's recorded? Or is it
you
just
can't
live?
see.
I cannot see anything.
Oh,
Any
okay,
recordings?
that's fine. Good evening to everyone and welcome to the SPM revision seminar online. And today's subject is physics. Before I introduce to the speaker, anyone who would like to ask a question answered by the speaker, please post your questions on the chat box so we can read them out during the Q&A session. Besides that, for the Form 5 students this year, we are still offering our School Achiever Scholarship Award, SASA. We do highly encourage all Form 5 leavers to submit your application through our webpage. For more information, please log on to our webpage to find out more. Today we have Mr. Eilham from the Faculty of University Foundation Studies as a speaker for today. Over to you, Mr. Eilham.
All right, thank you, Mr. Mohan, for the introduction. All right, welcome back, everyone. This is our week 10 for our SPM revision seminar. And also, of course, this is going to be the last topic, which is the last chapter, chapter 10, okay, for our SPM. Mr. Mohan, your mic is making sound. All right.
Yeah,
okay.
Sorry.
Okay, all right, okay, okay, it's okay. All right. So today we are going to continue with chapter 10. Okay, so let me share my screen. My second screen. Okay, so this is going to be our topic this week. Our topic is going to be on radioactivity. So hopefully everyone is ready. Okay, so now we are going to go through radioactivity. Okay, so radioactivity is the last chapter, chapter 5, form 5, or in your SPM syllabus, this is actually chapter 10. Okay, this is chapter 10, radioactivity. Sorry. All right. Chapter 10, radioactivity. All right, so we are going to browse through the chapter, the topic first, before we go any deeper. Okay. All right, so this is the things that we are going to talk about today. First thing we are going to look at is the composition of the nucleus, and then the radioactivity emission. Okay, we are going to look at the 3 types of decay that happens inside the nucleus. Okay, the first one is going to be alpha decay. Second one is going to be beta decay. The gamma decay. All right, so we have these 3 types of decay. We are going to learn to distinguish what are the difference between all of these kind of decays. Okay, and then we are going to look at the half-life of the nucleus. Okay, and also we are going to look at the uses of those decays, the uses of what we call as radioisotope. Okay, so we're going to look at what is those isotope. What is isotope actually? All right, so we are going to look at that. And last but not least, we are going to look a little bit on nuclear energy. We are going to try to define what are nuclear fission and also what are nuclear fusion. Okay, so let's get started. Okay, those are the topics. Okay, all right. So first thing first, let's look at the most basic thing that we need to understand. Okay, the first thing that we need to look at is the composition of nucleus. Okay, all right, so I believe you guys have learned in chemistry. Okay, this should be like the elementary thing that you're going to learn in chemistry is the picture of what an atom is. Okay, what is an atom? So this thing over here, this picture, this figure over here that I have, this is the description of a picture for an atom. Picture for an atom. All right. Just in case you guys are interested, okay, this picture of an atom, this is actually an incorrect picture. Okay, I can see that they are actually incorrect. In fact, nowadays we actually have a much more correct picture for atom. Okay, but for most of the time when we try to teach some basic things, we still use this model. This is called as planetary model. Planetary model. Okay, so planetary model actually is basically the model that we have using the concept of a planet. Okay, so the concept of the planet is that we have in the center over here, we have some sort of a center, and then all the electrons is going to orbit around the center, very much like a planet orbit around the star, okay, around a star. All right, so for this case, the center over here, this is called as the nucleus. Okay, and the nucleus are made up of proton and also neutron. Okay, so they're going to combine. Okay, and when they combine, they are going to create nucleus. All right. Electron, they move freely around the orbit. Okay, so this is the picture. All right, so the thing about this picture is that this picture actually have been disregard. Okay, we actually have taken this one away when you go into a much more recent theory. Okay, there is a much more recent theory which is called as the probabilistic model, which take the model of the electron, not like this, but instead it becomes some sort of a probabilistic model. Okay, so they are also sometimes called as a probabilistic cloud model. Okay, so this one is rather weird. I would for you guys to actually learn about this, you will need some sort of basic understanding in several things before you can actually go for this model. Okay, so for the time being, we are going to just use this model. This model is the simplest type of model that we have to actually describe an atom. Okay, so atom consists of electron, proton, and also neutron. Okay, and then electron is located at the outside. It can move. Proton and neutron usually make up the center, which is the nucleus or the nucleon, right? And then nucleons are usually placed in the center. All right, so this is how you describe the element that the element. Okay, so when you want to describe an element, you usually are going to describe it like this. Okay, this is the name of the element, and then you have 14 over here. This is the nucleon number. This is the proton plus with the neutron, and down here you are going to have a proton number P. Okay, so let's say you have an element X, and then you have, this is going to be the nucleon number, and this one is going to be the proton number. All right, so that is the kind of basic things that you're going to do. Okay, all right, so now after this, we are going to look at something called as isotopes. Okay, we're going to look at something called as isotopes. So what are isotopes? Isotopes are elements which have same number of protons, okay, but different number of neutrons. Okay, so if you remember, we defined X just now, our element, as the number of N nucleon and P. Okay, so we have N and also P. N is the nucleon and P is the proton number. All right, so you can have one element. Okay, you can have one element, but the element have different number of proton. Okay, so this one, you can take the analogy. You can take it like you have a car. Okay, let's say you have a let's use a Saga car. Saga is quite easy. Okay, Saga car. So you have a Saga car. One Saga car, it have some sort of let's say it have a stylish seat. Okay, so one Saga car, it have a stylish seat. Okay, so another Saga car, it doesn't have a stylish seat, but then it has a good engine. Okay, so a better engine compared to other Saga car. And then the third one, okay, so a stylish seat, good engine. Okay, the third Saga car, it doesn't have these two things, but it have a good paint. Okay, so when you look at it, you are going to be like amazed by the paint job. All right, so those are the three types of things. Okay, but essentially they are all Saga car. Okay, so they are all the same type of car, but then they have different characteristic. Okay, different characteristic, but then they are still the same item. All right, same item. Okay, now isotopes, they have same chemical properties. Okay, so the chemical properties are the same, but the physical properties are different. Okay, so well, just to revise your chemistry. Okay, so when you have an item, an element, okay, so element are usually going to be classified, identified by two types of things. First is their chemical properties, how they react with other things chemically, and the other one is the physical properties, how they look, and then how physical properties are usually based on how they look and what are the charge, the electron, those kind of things. Okay, all right, so here is an example that I can give you for an isotope. Okay, so first thing first, we have carbon over here. All right, carbon. Now, if you remember, carbon in your periodic table, carbon actually consists of 6 proton. Okay, carbon have 6 proton and then 6 neutron, and also it's going to have 6 electron. Okay, so now when we are talking about isotopes of a carbon, isotopes of a carbon can actually exist such that it have 6 proton, but then the neutron number actually differs. You have 7 neutron and also 6 electrons. So the number of neutron is different. Okay, so this is called as carbon 13. And then next we have a carbon 14. Carbon 14, it will have 6 proton and then 8 neutron and then 6 electron. All right. Okay. All right, so carbon 12, it is going to have 6 proton, 6 neutron. This is the normal. Okay, and then you can have carbon 13. This one is not really normal. Okay, it will have 6 proton, but then 7 neutron. Okay, this one is not really normal, but then this is still stable. Okay, now the next one is the carbon 14. Carbon 14 consists of 6 proton and then 8 neutron. Okay, so for this case, you are going to have 6 plus 8 is going to be 14. So the nucleon number is 14. Okay, so you're going to call it as carbon 14. Okay, 6 plus 8 is 14. And you can see over here, carbon 14, this is actually the radioactive one. Okay, carbon 14 is the radioactive one. What does it mean? Okay, so looking back at carbon 12, carbon 12 is stable, meaning that it can occur naturally on our planet. Okay, it can occur naturally. Carbon 13, it also is stable, but then the abundancy is only around 1% compared to carbon 12. Okay, carbon 12, they made up 98% of all the carbon that we have. Carbon 13, they make up 1.07%. But then carbon 14, these are the radioactive one. Okay, radioactive meaning that they are unstable. Okay, they are unstable. And when they are unstable, meaning that they are going to decay. Okay, they are going to decay to make them much more stable. Okay, so they are just going to be trace. They are not going to be abundance in our universe. Okay, so key point over here, carbon 12 comes from 6 proton plus 6 neutron. This is 12. Carbon 13 come from 6 plus 7. This is 13. Carbon 14 comes from 6 plus 8. This is 14. So we just add up the number of proton and also the number of neutron. Okay, all right. So if you are kind of wondering why don't we call it a new thing? Why don't we call this element a new element? Okay, because element is defined based on their proton number. Okay, when you have a proton number, 6 proton number and 6 electron number, that means that the item is carbon. Okay, so that's how we identify element. All right. Okay. All right, so when I talk about the unstable just now, the unstable element just now, oh sorry, the unstable isotope, sorry. Okay, so the unstable isotope that I mentioned, I says that it is going to decay and it's going to become a much more stable element. So unstable isotope. It is going to decay and it will become stable. Okay, so this is the general idea that you can have. Okay, and when it decay, it will sometimes give out an emission. Okay, it will emit some form of radiation. Okay, namely, you have three types of radiation. They are alpha radiation, beta radiation, or gamma radiation. Okay, and sometimes the product is called as alpha decay, beta decay, and then this thing is gamma decay. All right, so these are the three types of decay that we have. Right, and some books they use instead of decay they use alpha particle. Okay, they give up alpha particle, particle. Beta they give out beta particle, and then gamma they give up gamma particle. Okay, so these are just they usually refer to the same thing. Okay, based on the context of the words. All right, so I'm going to look at each and every one of these decay one by one. Okay, I'm going to show you what it means. Okay, and how this kind of radiation or this kind of decay are produced by those unstable isotopes. All right. Okay, so the first one is alpha decay. Symbol for alpha decay is alpha. This is alpha, all right? Okay, during alpha decay, a radioactive atom X will decay. Okay, so in most cases, an radioactive element X, like this one, it is going to decay. Okay, so this is the equation of the decay, and emits an alpha particle. Okay, so it will emit an alpha particle. So that alpha particle is actually a helium nucleus, right? So it is a helium nucleus over here, you can see. Okay, so for this kind of cases, you can see initially we have element X, we have start with X, A, and also Z. And then it decays, it decreases, and when it decreases, it will actually loses two things. Okay, it will actually lose. First thing that it's going to lose is it is going to lose 2 neutrons, and also it is going to lose 2 protons. Okay, so this is what happened when you have an alpha decay. All right, so you can see over here 2 neutrons, it doesn't have any charge. 2 protons, it have a charge. So this alpha particle is going to be a positive charge. Okay, so alpha particle, this is a helium, is going to be a positively charged particle. Okay, and in this case, atom X will lose 2 neutrons and 2 protons and becomes atom Y. Okay, so that is the general idea over here. All right, so let me give you an example, just in case if this is not really clear. All right. So the example that I want to give you is uranium. Okay, let me give you a uranium as an example. All right, so you can open up your chemistry textbook, try and go for the periodic table, try and check what is the proton number for uranium. Okay, so proton number is 92, and then the nucleon number is actually 238. Okay, so this is a uranium. And for most of you who actually watch a sci-fi movie, you might actually have heard that uranium is an unstable element. They are commonly used to make nuclear something. Okay, nuclear something. So this is actually true. Uranium usually decays to become thorium. Okay, thorium is TH. Okay, and this kind of decay are usually alpha decay. Okay, so when you have alpha decay, you are going to have a helium, okay, a helium nuclei, okay, a helium nucleus, sorry, a helium nucleus over here. Okay, so now here is an interesting question. how do you get from here up until here? Okay, how do you do that actually? All right, so to answer that, it is pretty simple. You look at the number over here. This number is 238. Okay, the number is 238. This is the nucleon number. Okay, number of proton plus neutron. Okay, 238 is number of proton plus neutron. And now you have split this 238 into alpha particle, meaning that now you are going to split this 238. You minus with 4 nucleus. They minus with 4 nucleus for proton and also neutron that you have already split, and that will give you 234. Okay, so this is the new number of proton plus neutron. Okay, so 234, that will be the number of this thorium over here, 234. Okay, all right. And then, okay, let me erase this first. All right. Okay, and then now you have 92. This uranium, it have 92 proton, but you have split it. You have removed 2, and you make that 2. You turn it into a helium. So it is going to be 92 minus 2. It will become 90 over here. Okay, so 90 over here. So how do you actually split them? You can imagine the uranium in the center. You have 238 combination of proton and neutron. Okay, and then you remove 4. You remove two proton, 2 neutron, and then you will get helium. Okay, helium alpha particle basically, and then the remaining element is going to create a thorium. All right, so now based on what I said just now, because the number of proton itself changed, now we can actually consider this to be a new element. Okay, because the number of proton now changed, it is going to be new element. All right, so this is the general formula. Okay, and this is my example. You can use any example basically. You can try and search for any alpha decay equation that you can find. Try to come up with the correct value for the nucleus number and also the proton number. All right. Okay, now we are going to look at beta decay. All right. So in beta decay, electron or positron, okay, is ejected from the nucleus. So during beta decay, this one is quite different. Okay, okay, all right. Okay, so this is the beta decay. During a beta decay, okay, in different to alpha decay, during beta decay, it is going to give out electron. Okay, it's going to give out electron or a positron. Okay, so electron is negatively charged, but then positron is actually a positively charged. Okay, so those are just the difference between electron and positron. But for your level, you are going to just focus on electron. Okay, you're just going to focus on electron. And also, this is just some additional information. In addition to electron, electron neutrino is also going to be ejected during beta decay. All right, so the whole process occurs as neutron is transformed into electron and proton. All right, so what will happen during beta decay in general, you can see. All right, sorry. Okay, so during beta decay, what is going to happen is that the center, okay, this is the nucleus, this is the outer electron, okay. During beta decay, the center is going to emit neutron. Okay, so it is going to give out neutron, but this neutron is going to be transformed into electron plus proton. Okay, but how is that possible, sir? I mean, that doesn't make any sense. Okay, so we know that neutron can actually, it can turn into electron and proton, because you can see neutron, the charge for neutron is 0. It is a neutral charge. Electron is a negatively charged. Proton is a positively charged. So negative charge plus positive charge is going to give out 0. So this is an equation that can can happen during this transformation. Okay, a neutron can actually transform into a electron and a proton. All right, so sir, I don't get it. How do you get that, sir? All right, so the thing about this is that neutron is not the most smallest thing yet. Okay, inside neutron, you can still split neutron and you'll get something called as quarks. All right, you'll got something called as quarks, and these quarks is the things that's going to change. Okay, it's going to change and transform into electron, and this quark is going to rearrange itself to become a proton. So those kind of things is going to happen. But if you guys want to make it simpler, you can just take that neutron can actually decay up to become electron and also proton. Okay, it can. All right. Okay, so this is the whole process. Now you have, this is the element E Z, this is the X is the element. Now when you have a beta decay, okay, beta decay, you are going to lose an electron. Okay, you're going to lose an electron. All right, so when you are losing an electron, that means that in order to balance this equation, you need to add you actually don't just lose electron, you also lose one negative one. Well, this is -1, so you are going to have to add over here on the number of proton over here. All right, so and then this is the electron neutrino. Okay, and as the process occur, you are going to lose electron and also proton. So you have proton loss and also electron loss. All right, so electron loss over here, and then proton loss over here. All right, so here's an example. I think I can just give you the example straight away. So I will put it over here. Let's say I have a PB, okay, a lead. All right, so PB, it have 214 and 82 as its proton number. Now let's say this lead, it will actually decay. All right, it will actually decay. So when you want to do the decay, you are going to have this PB to actually become a new element. Okay, this is a new element, plus with an electron, plus with a beta particle. It's not electron. We are going to call it as a beta particle. All right, so beta particle is 0, -1, and then this is electron, and then plus with the electron neutrino. I will just put it over here, neutrino, 0, 0, and then this is V. All right, so this is V electron. Okay, all right, so this is the electron. All right, so this is the beta particle, this is the electron neutrino. So now the question is, what is going to be this new element? Okay, what's going to be this new element? All right, so if you look at this equation, the number of nucleon, okay, the number of nucleus is going to still be the same. Okay, so it's going to be 214. It's going to be the same, but then the number of proton is going to actually increase, because we mentioned just now the neutron going to turn into a proton plus an electron. Okay, so this proton is going to add our value over here. So it is going to be, instead of 82, it is going to become 83. Okay, all right. Okay, and from here, because, okay, you see, it loses neutron, but it gains proton. If you try and add up the nucleon number will actually be the same. Okay, so no changes need to be done. Okay, but then you need to check on your periodic table what element have 83 as its photon value. Okay, what element? Okay, so the element that we have is actually called as bismuth. Okay, Bi, bismuth. All right, so the whole equation, if I may put it, okay, the whole equation is going to look like this. Okay, so this is going to be, we start off with 214, and then we have 82, and this is plumber or lead. It will actually become bismuth, Bi, and also this is going to be 214. This is going to be 83. Okay, so neutron, it turns into proton. Plus with the beta particle is 0, -1, and also electron. And then you are going to have electron neutrino. Okay, but I think on your level, you can just dismiss this part, because I didn't think I see this in any of the past year question. Most of them are going to just accept it like this one. Okay, but just for precautious, also add up the electron neutrino. Okay, all right, because this one is the correct part. All right. Okay. Okay, so recap, just in case you don't understand. In beta decay, you're going to have neutron. It's going to split into proton and also electron. Okay, the proton is going to increase the proton number, but the nucleon number is going to stay the same. Okay, the nucleon number is going to stay the same, because n is just n changed to p. So if you add them up, they are going to still be the same value. Okay, so the whole process is going to be a new element plus with electron plus with electron neutrino. All right, so those are the kind of things that you are going to have. Okay, all right. Next one is gamma decay. Okay, so gamma decay, in previous decay, all elements are trying to achieve some stable energy configuration. Okay, so the reason why they change from one element to another is because they want to have this stable energy configuration. Sorry. Okay, so stable energy configuration. But for gamma decay, the energy of parent atom is changed by emission of a photon. So for gamma decay, this is the symbol for gamma. For gamma decay, you are going to have the same element. Okay, same element. Nothing is actually going to change between these two elements. It's just that this element, we call this as the parent element. This one have a higher energy. Okay, this one have high energy. All right, so high energy. The thing is that we want to get those energy to lose, because we want a stable element. So it is going to give out some sort of radiation. Okay, this is a radiation. Okay, this radiation is going to carry out the excess energy, so that the element is still the same. It's just that the energy got lowered. Okay, the energy is lowered. All right, so for gamma decay, energy of parent atom, this is the parent atom, is changed by emission of a photon. Okay, so this is the photon that I mentioned. All right, so in form of gamma ray or short electromagnetic burst. All right, so in this kind of cases, when you have a gamma decay, it is going to be a short but deadly. Okay, it is going to be short, but the amount of energy is huge, so it's going to be deadly. Okay, so it is going to lead serious problems for biological material, because in our cell, okay, our cell if we allow ourselves to get in touch with this gamma radiation, it is going to cause some sort of health problem, such as cancer, I believe. Right, cancer is one of them. All right. Okay, so this one is decay for stability. So the main reason why we study radioactivity is, of course, to check for the most stable configuration element. Okay, so some elements, when we discover them, they are not really that stable. Okay, they do exist, but they exist as that element, but they will decay into other element. All right. So as atom transform into another element, the new element might be unstable. Okay, so this is a continuous process. All right. So for example, you can start off with uranium. For example, we get uranium just now, 238. Now uranium, if you remember from my previous example, it will become thorium, TH. Okay, TH I think is 236. I don't remember the value now. But then thorium itself is still not stable. Okay, so when this is not stable, it decay, it become less energy, but then this one is still not stable. This one will still decay. Okay, so the decay process is going to continue to happen, continue and continue, up until when you get Pb. All right, so starting from uranium, it's going to decay up until Pb. All right, so Pb is considered as the stable element for this uranium. Okay, all right, so here is an example for the decay. There is a graph that I can show you. This is the graph. Okay, you can see we start from uranium over here. This is uranium. It changed to thorium, and then it changed to Pa. I don't remember what Pa is, sorry. And then it changed back to uranium. But now this uranium have lower energy compared to the previous uranium, because 238, this is 234. Then it will decay again, decay. This is the whole process. And then up until here, you will get Pb or lead. Okay, starts from here, it end up here. All right, so why does this picture looks very weird, sir? I don't get it. Okay, so this picture looks like this, okay, while most graph is going to go up like that, but then this graph is not like most graph. This graph is actually a graph of radioactivity. So for this case, you can see when the arrow is going this direction, that is actually an alpha decay, meaning that for this kind of cases, it is going to emit what kind of radiation? You are going to have alpha particle emitted. So you are going to have 4,2, and this is helium. All right, 4,2. Okay, this is 4,2, and then when you have this beta decay is going to go from left to right. So beta is going to be emitting an electron, -1 electron, and also the tau neutrino. Electron neutrino. Sorry. Okay, so electron neutrino. Okay, electron neutrino, and the whole process is going to repeat up until it becomes lead. All right, so if you are interested, you can actually study this. This is a very interesting branch, because this one allows you to actually understand chemistry in the eye of physics, right? Okay. Okay, now we are going to look at the characteristic for alpha, beta, and gamma particle, the radiation just now. Alpha particle, the nature is that the alpha particle itself is the nucleus of helium. So we have 4, we have 2, we have He. Okay, so remember, even though this is a helium, this is not helium atom. Okay, remember why? Because when the decay process occurs, we did not give out electron. No. Okay, electron is not give out. So the only thing that we give out is the proton and also the neutron. So when you have that, that means that this is going to consist of proton and neutron only. Okay, you are not going to have any electron. All right, so this is why I put over here nucleus. Okay, so nucleus of helium, meaning that this is not atom, a helium atom. No, this is only a nucleus, a proton, a combination of proton and neutron. Okay, for beta particle, we have beta particle is electron. So the electron should have high speed because it have quite a lot of energy. And for gamma ray, they are just a photon. Basically, a photon, or we are also known that as electromagnetic wave. This one can also be changed as photon. All right. Okay, so what is the charge for this alpha particle? You have 2 proton, 0 electron, so the charge is going to be positive 2. Okay, for beta particle, this one is okay, so just in case you don't remember, this is He, this is 0, -1, this is electron, this is just some gamma radiation, right? So electron, the charge is -1, and gamma ray, the charge is neutral. All right, so ionizing effect. Alpha particle, it have a strong ionizing effect, meaning that if you place this onto some stable, it is going to ionize other elements. Okay, so because this is a +2, so +2 charge is going to ionize other element because of the extra charge. -1 is going to be a weak ionizing effect because -1, the charge is not really as strong as +2, so it is considered weak. But for gamma ray, it doesn't have any charge, so it is not going to ionize that good. Okay, it's going to be a weak charge, weak ionizing effect. Okay, so alpha particle, this one you will need to actually remember. Okay, so for alpha particle, if you have an alpha particle going onto a piece of paper, let's say that this alpha particle move onto a piece of paper, it cannot go through this piece of paper. Okay, so the alpha particle cannot penetrate a writing paper. It is going to be absorbed by the writing paper. All right. And for beta particle, the electron can pass through a writing paper. Okay, it can pass through, but it can only pass through about 5 millimeter aluminum. So it cannot really penetrate metal. Okay, but for gamma ray, okay, this one is interesting. Gamma ray, because the energy is so high, the gamma ray can actually pass through lead. Okay, it can pass through metal. Okay, so 25 millimeter of lead reduces the intensity of the gamma ray by half. Okay, and from here, just in case if you guys are interested, this is the reason why we have a bunker in those countries that have nuclear energy. They created a bunker that is just as a safety measure for in case, you know, something bad happened to their nuclear power plant. Okay, so they have a bunker. Bunker is usually placed with some sort of lead, some sort of isolated room, and that isolated room is going to have those wall around them. Okay, walls surrounding them. All right. Oh, sorry, I should just erase all. Okay, and now deflection in electric field. Now, electric field and magnetic field, if you remember, because this is a charged particle, so charged particle is going to be deflected by electric field. Charged particle is going to be deflected by magnetic field. This one, I recommend you to go back to the previous chapter, the chapter involving the hand rule, right hand rule, left hand rule. Okay, so we have talked about that, how when a charge is moving and it meet up with, for example, magnetic field, it is going to be affected by magnetic field. Okay, it's going to be either attracted to it or, you know, deflected by it. Okay, so these two have charge, it's going to be deflected. All right, so but for gamma ray, because it doesn't have any charge, so when a gamma ray pass through electric field, it is not going to deflect. Okay, and again, when we are talking about the speed, okay, so alpha particle, because you can imagine alpha particle is carrying a proton and nucleus, a proton and neutron, so the speed is usually lower compared to beta. Okay, beta is just electron moving, so this is going to be 90% of speed of light. But gamma ray, because this is actually a photon itself, so it's going to move at the speed of light. All right. And this one is half-life. Half-life is basically time taken for half of the atomic nuclei to decay to other elements. So for this case, I'm just going to give you a simple example, which is copper. All right, so CO. Oh, sorry, CO is, I don't think CO is copper. CO is cobalt, I think. It's not copper. Cu is copper. Cu is, yeah. All right, so CO is going to decay up and it will become Ni, nickel. Okay, and it's going to give out an electron and also electron neutrino. All right, so here's a question. What kind of radiation is this? Is it alpha, or is it beta, or is it gamma? All right, so we're going to discuss the answer later. All right. Okay, so according to the decay, okay, according to what we have in our lab, copper is going to decay into Ni, nickel, okay, and that nickel is going to be not really that when it first decay, it can actually decays up until this energy level or this energy level. All right, so there are, for this energy level, the energy is quite high. Okay, so when the energy is quite high, the energy can still be reduced. Okay, this is actually another type of decay that we have mentioned just now. This is actually a gamma decay. Okay, this is actually a gamma decay. So the nickel, this is the parent, is going to decay up until it becomes this this daughter element. And this daughter element, it can still decay, it can still become much more stable. So it is going to decay up until this energy. All right. So for half-life, it is the time taken for atomic nuclei to decay. So in CO60 decay, they are going to take around 5.27 years to actually decay half. All right. So for example, you have 10 gram. After 5.27 years, it's going to become half of that 10 gram. It's going to go 5 gram. Okay, and another 5.27 years is going to become half. It's going to become 2.5 gram. Okay, it's going to continue up until certain time period where it's going to reach up until 0. Okay, and okay, so these are just some simple uses of radioisotope. Carbon-14 is used for study of artifact and radiocarbon dating. So carbon-14 radiocarbon dating. Okay, so that one is very, very common. Okay, radiation are used for food inspection and also monitoring thickness. Okay, remember one of the particle emitted can actually pass through paper, so we can use them to monitor the thickness of the paper, and also underground leakage, because they can, one of the radiation can pass through the plum, okay, the metal, sorry. Okay, cobalt-60 are commonly used in radiotherapy or cancer treatment. So because cobalt-60, the energy, as I mentioned just now, the energy for cobalt is gamma ray, and gamma ray is a high burst, so it can have impact on our cell. So they are usually used in cancer treatment. Okay, phosphorus-32 is used as tracer to study plants. Gamma rays from radioactivity kits used to kill bacteria in food. So this one is just for you guys to know. Okay, now we are going to look at nuclear reaction. As I mentioned, nuclear reaction, this one is going to be very, very short. Okay, so nuclear reaction, we have two types of nuclear reaction: nuclear fission, and the other one is nuclear fusion. Okay, so in nuclear reaction, in most cases, you are going to have a parent particle, and something will happen to this parent particle, and it is going to create a daughter particle. Okay, so nuclear reaction is going to have parent particle. Parent particle is going to be changed into a daughter particle, and then you are going to have some sort of energy in the process itself. Okay, so there are two types. First is nuclear fission. The other one is nuclear fusion. All right, so let's see what is nuclear fission. Nuclear fission involves the splitting of heavy nucleus into two nuclei of roughly equal mass and neutron as a byproduct. So unlike decay, now we have, for example, this is uranium 92. Okay, now this is a uranium. Now you split this uranium until it becomes 144. This is Ba. Ba, I think, is barium. Kr. All right, so I can already write Kr. This is 89. This is 36. Okay, so you make sure that this plus with neutron, sorry, 10 neutron plus energy. All right, so this is the byproduct. Okay, so you are going to have this parent. This is a parent. You are going to make a new daughter. Okay, new daughter. This is like a splitting of the nucleus. Uranium, you're going to split into barium and also Kr. I don't know. I don't remember what Kr is. Sorry. So Kr, and another byproduct is a neutron. Okay, so try and make sure that the value actually equal. Okay, 144 plus 89 plus 1, make sure they are 235, and also 56 plus 36 plus 0 is 92. Okay, so these are the kind of fission. Fission usually refers to splitting. Okay, and then this energy, this is the energy that we are usually referred to when we are talking about nuclear as a source of energy. Okay, this kind of energy is so huge that we can use them to fuel the entire country's energy consumption. Okay, all right. Okay, all right, sorry. The other thing is nuclear fusion. Okay, and as how the name goes, fusion happens when you have two small nuclei and they come together to form a heavy nucleus. Okay, so the fusion is more difficult to achieve because because if you think about it, nuclear fusion happens when you have two nucleus. They try to combine with each other. Okay, this is two small nucleus. They try to combine to become a heavy nucleus. Now, in order for this to happen, you need to remember that this nucleus consists of proton and neutron. This nucleus consists of proton and neutron. If you try to combine proton and proton using electrical knowledge, positive charge and positive charge, it's not going to actually, it is going to repel. Okay, it's going to repel. So in order for you to allow this to happen, you will need to have enough kinetic energy to overcome the electric repulsion, and most of the time the kinetic energy can be obtained from heat. Okay, from heat, and that is why the nuclear fusion actually happen only most common we can see them are inside of a star. All right, so this is an example. You have one, this is a hydrogen. Okay, this is an hydrogen isotope. This is another hydrogen isotope. You try to combine these two hydrogen. Okay, so 2 plus 3, you are going to combine and make them 4. Okay, and then 1 plus 1, combine them, make them 2. And then you give out 1 neutron and also a burst amount of energy. So this is the equation that represents that. Okay, so why do you say that the energy is going to be very big, sir? We didn't catch that. Okay, the energy is very, very big due to the fact that Einstein himself says that E is equal to mc squared, meaning that if the mass is very, very small, let's say, for example, 1 gram, which is 0.001 kilogram, you multiply with the value of c squared. Okay, c is the speed of light, which is 2 times 10 to the power of 8 meter per second squared. Okay, 2 times 10 to the power of 8, and then you square that and then you multiply. You are going to get a huge amount of energy just based on 1 gram of this kind of things. Okay, so that's why we say for nuclear energy to happen, the energy is going to be very, very big. All right. Okay, so all right, so this is some question for you to think about. All right, so first question, which particle should be used to detect underground leakage? Alpha particle, beta particle, or gamma particle? Okay. And second one, where does the sun generate its energy? Is it through nuclear fission or nuclear fusion? And the third one, is it true that alpha decay will give out helium atom as its alpha particle? All right. So try and think up of this question over here. Meanwhile, I will give our session back to Mr. Sabah, okay, for a short break. Sorry, Mr. Mohan, sorry, not Mr. Sabah today, Mr. Mohan. All right, so Mr. Mohan,
Sure.
back to you.
Okay, thank you. Over to you, Mr. Eilham.
All right, thank you, Mr. Mohan. Okay, so now let's try to answer this. Oh yeah, before that, I actually asked you this question before. Where's the question this time? Oh, I think I have deleted the question. Oh yeah, this is the question. All right, so I asked you guys what type of decay is this? Okay, so for those who answered this as a beta decay, congratulations to you guys. The answer is beta decay. All right. Okay, so for those of you who actually answered this as beta decay, okay, congratulations. And then to answer this question, which particle should be used to detect underground leakage? The answer is gamma particle. All right, so gamma particle should be used to detect underground leakage because only gamma particle among this type of particle that can emit can actually pass through a metal. Okay, and then where does the sun generate its energy? So the sun generates its energy by nuclear fusion. Okay, so if you look at the notes, nuclear fusion involves combining the hydrogen into helium. Okay. All right, and then in order for that to be achieved, you will need extra heat. So that is why the sun is very, very hot. Okay, so the third question, is it true that alpha decay will give out helium atom as its alpha particle? So the answer for this one is wrong. Okay, so the thing over here is that it will not give up helium atom, it will give up helium nucleus. Okay, so the keyword over here is actually helium nucleus instead of helium atom. You don't have electron, so you cannot call them as helium atom. All right. Okay, so let's see if we have any question for today. Do we have any question from Okay, all right. So I don't think we have any questions. So I think we can proceed now. Okay, so we don't have any questions. So I guess we can just proceed to end our class for this week. Okay, Mr. Mohan, back to you.
Okay, thank you, Mr. Eilham. Hopefully students, you have learned something and you have a clear thought about this session. And tomorrow's session will be English with Miss Aishwari. So stay tuned for tomorrow at 8 p.m. and see you all tomorrow. Good night, everyone.